Another useful command is the db command. It stands for display bytes. If we want, for example, to display the bytes at address ESI, we could just use this command, db ESI. And we get the bytes at location ESI. As ESI points to the beginning of source list, we actually see the bytes inside source list. Of course that we see them in the little endian convention. This is why they show up in the reverse order. Just as a comparison, we can see that source list contains 1, 5, 8, 2, and so on, which is exactly what we can see here. 1, 5, 8, 2, and so on. The db command is in fact just one command out of a family of commands. All those commands begin with D and then another letter, which corresponds to the chunks of data which you want to see. db is going to show bytes. If you wanted to see words, you could use dw. In this case, probably the best choice would be dd, which is going to show D words. Now we can really see the D words inside source list. 1, 5, 8, 2, and so on. Note that when using dd, we don't have to worry about little endian conventions. We just get the D words. By the way, if we take a look at EDI, we are just going to see zeros. This is the destination list and we haven't initialized it with anything. Usually, when the program begins, it will just contain zeros. Instead of using those commands, we could use the memory window. View, Memory. This gives us this window. We could clip it here. It is your choice how to order your windows. You could, for example, put it anywhere that you want. At this point, the memory window shows us the contents of the memory at those addresses. The addresses are shown on the left. The other numbers are just the contents of the memory in those addresses. If we wanted, for example, to view the memory at location ESI, we could just write ESI here, in the virtual text box. Then we get those bytes, which are exactly the bytes of source list. If we type in EDI, as expected, we just see the zeros. There are a few display formats for the memory window. The first one, which we currently use, is byte, or maybe bytes. We just view the data as simple bytes. Sometimes a different display format would be more useful. It depends on the case. In this case, since we are viewing D words inside an array of D words, a wise choice would be long hex, where we can see the hex values of the D words, just like with the dd command. By looking at the code, we know that the values of ESI and EDI are soon going to change. That is because we use the instructions loadsd and also stosd. If we want to be able to follow the contents of the arrays, maybe for example to follow the contents of the dest list or maybe of source list, we would have to pick a number instead of putting a register here. That is because ESI is going to change, and then we will not have a full view over the array. We could, for example, find out the current value of ESI and maybe the current value of EDI and just put in those numbers. which gives us currently exactly the same result. However, when ESI changes, we want to keep viewing this part of the memory. As an important comment, you could have more than one memory window. In this example, we want to have two memory windows. So let's open another one. View, Memory. As we can see, the graphical interface messed up. Let's fix it. We take this window, which is the memory window, take it out for a moment, and now try to clip it here. This is the way I wanted it to be. If you want to do something else with the windows, feel free to do it. At this point, the first memory window shows us the contents of source list. I want to view dest list in the other memory window. I'm going to read the value of EDI, which currently points to dest list, copy this number, and paste it here. I also want to change the display format into long hex. The dest list is currently made of zeros. Basically, during the program, we expect those values to be copied somehow into those locations. We expect that here we are going to have the value 2, and here we will have the value 6, and here 9, and so on. After all this talking about memory, you might be wondering if there is any way to get a map of all the memory of the program. In fact, there is a way. It is called the lm command, or maybe list modules. I press the return key, and now I get an interesting table of different modules inside this program. Let me list the columns. The first one is start. Next one is end. And then we have the module name column. The module name is actually just the name of the module. This is our module. It has some really strange name. Modules are basically just binary chunks, or maybe binary files. They are just like executable files in some way. You might be wondering how come we have so many modules if we wrote only this code. Some of those modules are necessary for the operation of our program. As an example, NTDLL is necessary for almost any Windows program. Kernel 32, for example, is used here for the exit process function. The exit process function really resides inside this module. We also have, for example, the MSVCRT module, which helps us with printing things to the console. We use some function inside this module called printf. You don't see it inside this source code because it is somewhere inside training.inc. The start and end columns specify the start address and end address of every module. As an example, our module begins from this address and ends at this address. Now that we know how to view bytes in different locations, let's try to see what we have at this location. We copy this address, and then we use the db command to view the memory at this location. We can see that we have many strange bytes at this point. However, if we take a look at the textual representation, we can see something familiar. We can see MZ and also the famous string this program cannot be run in DOS mode. By now you probably know that this is just the beginning of a usual executable file. We can try to move on a bit and maybe add about 1000. We take again this address, use the db command, and add 1000. We could use this syntax, and WinDBG is going to calculate it for us. I press the return key, and now I can see some different part of the memory, and it is also pretty familiar. This part is actually source list, and we can also see it here in the first memory window. By the way, those are exactly the same addresses. We can see that this address is exactly the address which we have calculated. Let's try to move on another 1000. We copy again this value, but this time we add 2000. And we got to some location which only contains zeros. If we take a look at the second memory window, we can identify this part as the destination list, which we already know that it is all zeros. Basically, this part is where the BSS section begins, and the previous part here is the place where the data section begins. Let's continue a little bit more. I copy this command, and this time I'm going to add 3000. I get as a result some really strange bytes, and this time the textual representation doesn't really help me. A good guess would be to think that this part is the code section, or the text section. But how could we know? How could we know for sure? We could use the U command. U stands for unassemble, and it allows us to parse bytes as code. Let's use this command over this address. And we get a few instructions. Note that those instructions correspond exactly to the instructions inside our source file. We have here move ESI, some number, move EDI, some number, and finally move ECX 9, which correspond exactly to those three instructions. You might be thinking that the unit has some kind of magic inside of it. Or else, how could it know that those are instructions? In fact, the U command is not really smart. It can only parse instructions. However, it does not have the ability to decide whether some part in memory is code or data. This is a really hard question. Maybe only humans these days are capable of deciding those kind of things. If I try, for example, to use U on some other location, which is not code, maybe for example, here, I'm also going to get a few instructions, but they are going to be really strange. And this is because this part is not code. You have to pay attention yourself and make sure that you use the U command in the right places. If you use it in a place which is not code, you are going to get strange results, like this.